Here, we're going to go over some questions that seem to cause issues in the chapter 6.4 and 7 homework. So this one was number 2 in your homework, and you can see where it's taken from in the textbook with the question next to it. Take a moment and read through this question. Now we're looking in part A for the probability that an individual distance is greater than 204.30 centimeters. If we look at this, because they're asking us about an individual, we're going to still use the population information. So essentially, we're going to do the same exact thing that we did back in section 6.2. So if we look up at the problem, our mean is 195 centimeters, and our standard deviation is that 8.6 centimeters. So I'm going to walk you through how to sketch it out and use our calculator to do this. So I always sketch out my normal distribution first. That mean was 195. We're looking for an individual distance that's greater than 204.30 centimeters. 204 is definitely bigger than 195. And then because they're asking me for a probability, they're really asking me for an area. Remember, area, probability, and percent are all the same thing. And we want the probability that it's greater than this amount. So that means we want the area above or to the right. To do this in our calculator, we're going to use the normal CDF function. Remember from before, to get there, you hit second distribution, and then choose option 2, which is the normal CDF. When we do that, you enter the lower limit first. Sometimes you're prompted for this depending on which calculator you have. So the lower limit, the lowest thing that covers that area, is this 204.30. Then we want our upper limit. Well, this keeps going all the way up to positive infinity, but we can't type that in our calculator, so we usually just type in a whole bunch of 9s. Then we type in the mean, which is 195, and our standard deviation, which is 8.6. When we do that, we end up with 0.1397606,796. And then our directions on this question asked us to round to 4 decimal places, which gives us about 0.1398, because that 6 tells us to round up. So there's a 0.1398 chance or probability that an individual overhead reach distance is greater than 204.30 centimeters. If we look at part B, they're asking us to find the probability that the mean for 20 randomly selected distances is greater than 193.20 centimeters. So for this one, we're looking at a sample. So because it's a sample, we want to use that central limit theorem that we learned about in this section. Remember, to use the central limit theorem, we either need a sample size that's greater than 30, which we do not have. We have a sample size equal to 20, or we need the population distribution to be normally distributed. And we do have that here. They told us in the original problem that it's normally distributed. So we can use the central limit theorem. That tells us that the mean of our sample means is the same exact thing as the population mean. So we're still going to use 195 centimeters as our population mean. The standard deviation of our sample means is the population standard deviation over the square root of n. So we have to do an extra step here to find our new standard deviation. We're going to do 8.6 divided by the square root of 20. And when we do that, we end up with 1.923018461. So if we're trying to picture what's going on, we still have our normal distribution. The mean is still what they gave us in that original problem, 195, but this time we're looking that it's greater than 193.20. So that 193.20 is down here, and I still want greater than, which is telling me to find the area to the right or above. So because I'm finding area, I'm still going to use that normal CDF. My lower limit is 193.20. I'm still thinking of going towards infinity, but I can't type that in, so I type in a really big number. The mean is still 195, but that standard deviation is what we calculated it to be. When we do that, we get a probability of 0.8253707514. And same idea, they asked us to round to 4 decimal places, so we say that that probability is about 0.8254. If we look at part C, they asked us why could we use the normal distribution in part B even though the sample size does not exceed 30. So whenever they're asking us about that, they're really asking us why could we use that central limit theorem. And like we talked about up in part B, it's because the population was normally distributed. Now, if we keep going, another one that covered topics from section 6.4 that some students were struggling with was number 5. So let's look at this. An airliner carries 350 passengers and has doors with a height of 76 inches. Heights of men are normally distributed with a mean of 69.9 inches and a standard deviation of 2.8 inches. If we look at part A, it says if A male passenger is randomly selected, find the probability that he can fit through the doorway without bending. So in this question, we're still looking at only one passenger because of that word A. So that means that we're going to use everything from the population. So we're going to use that mean of 69.9. We're going to use that standard deviation of 2.8. If I sketch out my normal distribution to get an idea of what's going on, my mean is always smack in the middle. And when we're being asked to find the probability that he can fit through the doorway. So if we look back up at the problem, they're telling us the doors have a height of 76 inches. So that 76 inches is my data value. And if this person can fit through the doorway, they have to be that tall or shorter, right? If you're too tall, you'll have to bend over. You won't be able to fit through it. Now, we're still being asked to find a probability, so we're really looking for an area, which means we're still going to use that normal CDF. Now, in this case, our lower limit is all the way over here, down at that negative infinity, but we can't plug that in our calculator. So we plug in a negative, really small number, so negative and a whole bunch of 9s. Our upper limit, where that area stops, is 76. That mean is 69.9, and the standard deviation is 2.8. When we plug that in our calculator, we get 0.985318292. And I do want to point out some of these numbers towards the end might be slightly different depending on how many 9s you typed in, but the ones at the beginning should be just fine, which is okay because we need to round anyway. That 1 tells us to round that 3 down. It stays exactly the same. So we end up with 0.9853 as our probability. And that high probability makes sense because this area does cover most of that normal distribution. If we look at part B, they tell us if half of the 350 passengers are men, find the probability that the mean height of the 175 men is less than 76 inches. So this 175 is just that half of 350. So they did the math for us there. But if we think about it, we're no longer talking about one man. We've got a sample. So because we have a sample, we want to try to use the central limit theorem. So we need to check for those two requirements. In this case, our n definitely is greater than 30. Our sample size is greater than 30, so we could use the central limit theorem. But even if we had a small sample size, we could use it because the population's normally distributed, so it meets both requirements. Remember, when we use the central limit theorem, we're looking at the mean of the sample means. That's always the same as the mean of the population, so that's going to stay that 69.9. However, the standard deviation of our sample means always changes. That's our population standard deviation divided by the square root of n. So our population standard deviation was 2.8, and our sample size is 175. When we plug that division in our calculator, we end up with 0.21166,01049. So now, if we picture what's going on, we've got our normal distribution. We still have our mean of 69.9. And in this case, we're looking for the probability that the mean height of this 175 men is less than 76 inches. So we essentially have the same exact sketch that we had before, because less than is still telling us to the left or below. So we're still going to try to find the area. So we're using our normal CDF. Our lower limit is still that very small negative number. Our upper limit is still 76. Our mean is still 69.9. But now we have to use that standard deviation that we got using our central limit theorem. When we do that, if you plug it in your calculator, you just get 1 back. And it makes sense that this probability is even higher because notice the standard deviation. It's even smaller. So that 76 is further to the right than it was in part A in comparison to our means. If we look at part C, it says when considering the comfort and safety of the passengers, which result is more relevant, the probability from part A or from part B, and why? So essentially we need to think about what's going on here. If we're thinking about going through a door, one person goes through a door at a time. It's not like a group of people that's on an elevator. So because of that, we're going to think about that part A. So we would say it's the probability from part A because it discusses the proportion of the population that will be able to fit through the doorway. If you think about it, we don't care about if 20 people can fit through the doorway. We care about how many people can fit through the doorway, how many individual people. So that's why we want part A that deals with the probability of an individual person. If we look at part D, they ask us when we're considering the comfort and safety of passengers, why are women ignored in this case? And if you think about it, we're discussing the height of people, right? Who can fit through a doorway. So in general, men are taller than women. So if it works for a large proportion of the male population, it'll also work for a large proportion, likely even larger, for the women. And I want to clarify that first sentence. It's men are on average taller than women. We'll definitely know some women that are taller than some men, but on average, men are taller. So we'll stop there for the 6.1